Good morning. We already done or finished a lecture on silica refractories. We finished 2 lectures on alumina silica. So now I have 2 lectures on basic refractories. And there's these 5 groups here: magnesite, dolomite, chrome magnesite. Then there's this forsterite and the spinel. So we'll go over. We should be having enough time to go over magnesite and dolomite today. And then next week, we'll do these other 3: chrome magnesite, forsterite, and spinel. And we'll same format for all of these, the raw materials, the phase diagrams, a little bit about how these materials are processed, what kind of microstructure results, and then a couple of the key properties. So one of the raw materials for an MgO-based refractory is magnesium carbonate. The mineral is known as brunerite, and that's MgCO3, so it's magnesium carbonate. And there's 2 types of deposits: a crystalline deposit, and then a much finer crystalline deposit, a cryptocrystalline deposit. So these are about 88 and 85% MgO, and then the balance is CaO, Fe2O3, Al2O3, and SiO2. Usually Fe2O3 and SiO2 are the impurities in the largest amounts. So the crystalline deposits are fine to quartz crystals, and then the cryptocrystalline deposits are very fine crystals. So the carbonate is basically known as magnesite. Magnesium hydroxide, that mineral is brucite. That's MgOH2, so it's a hydrated magnesia. It's very scarce, so it's not a viable source for MgO. So for either brucite or brunerite, this is what happens when you heat them up. They're both going to decompose. So the magnesium carbonate, MgCO3, at 650 degrees C, the carbonate, MgCO3, decomposes to MgO and then the CO2 gas. And the magnesium hydroxide, brucite, MgOH2, at 300 degrees C, it decomposes to MgO plus the water vaporizes off. So as long as you calcine above these higher temperatures, higher than decomposition, you're going to end up with a fine particle size MgO. The main source of, one of the main sources of magnesium oxide is seawater or brine wells. So in seawater, there's 0.013 weight percent magnesium in seawater, and it says magnesium chloride, and it's also contained in brine wells. So we'll just look at the seawater precipitation process. So this number, 0.013 weight percent, turns out to be about 1 gram of MgO per liter of seawater. So the magnesium chloride, MgCl2, is in solution in seawater. So you take the seawater, which contains MgCl2, to that you add lime, CaO. So the lime reacts with the chlorine and forms calcium chloride, and that stays in solution. But the magnesium precipitates as the magnesium hydroxide, MgOH2. So you take that precipitate, you calcine it. The final calcination temperature has to be quite high, greater than 1900 degrees C, and you end up with a dense MgO material. It has a high melting point, 2800 degrees C, so it's a very refractory material. So you take this magnesium hydroxide, you calcine it at about 950 degrees C. So now you end up with fine particle size MgO. Then you press it into pellets, and then you have to do what's known as dead burning. You heat treat it from 1600 to 2000 degrees C, and that makes dense MgO. Crystals grow. You reduce the porosity, reduce the grain boundary area if you grow the crystals, and the density ends up to be about 3.25 grams per cubic centimeter. So dead burning makes it inert to other processes like hydration. So MgO is subject to hydration. It doesn't hydrate at a very fast rate. The kinetics are slow, but you dead burn it to make it inert, reducing the surface area and making a material that's more hydration resistant. So this is the effect of dead burning. Here's specific gravity. This is crystal size, and this is hydration tendency as a function of temperature. And it goes from about 1300 to 1650 degrees C. So this is temperature degrees C, 1/2 hour. So each one of these points was the material held, the MgO powder held at 1.5 hours, 1/2 hour. So specific gravity, it starts out at 3.5, goes to 3.6. So as you increase the temperature, the material gets denser. And the crystal size, this is the diameter in millimeters, 0.02 to 0.06. So the crystal size is increasing with temperature. And this is percent weight loss. So this is the loss on ignition. So the higher the weight loss, the more of the material is hydrated. So this material for hydration tendency is exposed to water vapor. I don't know exactly what condition it is here. Could be in an autoclave under steam pressure. I'm not exactly sure, but it picks up water and hydrates. So it picks up more water at the lower temperature than at the higher temperature. So this material was subject to some type of hydration test at 1300 C. And when they did the loss on ignition, there was 9%. So this material hydrated severely, but then the loss on ignition decreases. And at 1650, there's 1% or less. So the hydration tendency decreases with increasing temperature. But overall, MgO is pretty hydration resistant. It will hydrate somewhat if it's stored a long time before it's used. So this is magnesium oxide from seawater. There's a regular version and a high purity version. The regular version is 95 to 98% MgO. The high purity is over 99%, 99.5, 99.8. So it's high purity MgO. CaO, Fe2O3, Al2O3, and SiO2 are the main impurities in the seawater MgO. I've just listed more for reference here, different types of MgO materials and their chemistry and weight percent. So MgO is the primary component, and then we have CaO, Al2O3, SiO2, Fe2O3, and in a couple cases, MnO2. So the first three are magnesites, and where they're from, Austria, Brazil, and Greece. These are the magnesium carbonates. Then there's 3 seawater MgOs, one from Ireland, Japan, and United Kingdom. They're obviously made from seawater. And then there's 3 from brine wells, USA, Netherlands, and Israel. And then there's 3 fused MgOs, and these are melted and cast, allowed to cool them. During cooling, the crystals grow in size. So it doesn't matter which one of these routes you make the MgO, they're in the final stage, they're fused. So you can look at the MgO contents. This is the lowest one at 90. The fused material is 99.9. One of the advantages of fusing at high temperatures, during the melting process, some of the impurities evaporate and it becomes more pure. So the fusion materials tend to be pretty good purity. This one's exceptionally good. So you have these raw materials and they have various impurities. And one of the important ratios in an MgO refractory is the lime to silica ratio. So 1.86, the lime to silica ratio greater than 1.86 is what you want. And I'll go over this in some detail in a few minutes, but it's more desirable to have a lime to silica ratio greater than 1.86. If it's less than 1.86, there's a series of low melting compounds that can form. So this one's 3, that's greater than 1.86, but this one's less, 0.5. So this material can develop some low melting compounds as well as this one and this one and this one. So it doesn't mean it's not a useful refractory, it just can't be used at extremely high temperatures. So during the dead burning process or the fusion process, you're going to increase the crystal size. So the larger the crystal size, the better the corrosion resistance. So the bigger the crystals, the smaller the amount of the grain boundary area. So grain boundaries are where the impurities are concentrated. And when it comes to corrosion, that's the area that's attacked first. So if you eliminate the grain boundary area or try to minimize it, that is going to improve the corrosion resistance. So the dead burned MgO is dead burned at temperatures greater than 1900 degrees C. It's usually calcined first and then dead burned, but that multiple step process results in large crystals. And then the fused material, MgO, melts at about 2800 degrees C, so you have to melt it at a higher temperature. I mentioned that process vaporizes impurities. And then if you slow cool it, you can grow very large crystals and crystals greater than 1 centimeter in diameter. So they're fairly large crystals. So in these photographs, A, B, and C are sintered materials, and D is a fused material. So this marker is 100 microns. So A, B, and C going in that order, there's an increase in the calcining temperature. So A is calcined at a lower temperature than B, and B is calcined at a lower temperature than C. But you can see in A, the particle or the crystal size, you can make out the individual crystals. You can see grain boundaries. You can see some pores. The crystal size is less than 100 microns. When you go to a higher sintering temperature, they're on the order of 100 microns, and you can clearly see the grain boundaries and the internal porosity. And then the higher temperature for calcining, these crystals look like 200 or 300 microns in diameter. You can see the internal pores that have not been eliminated during sintering. And then you can see the grain boundaries and some of the impurities that are located at the grain boundaries. And D is a crystal or part of a crystal from a fused cast process. There's no grain boundary here. The crystal is larger than the field of view here. So these are probably large centimeter-sized crystals, but it still has some internal porosity. So we need to look at the MgO, CaO, SiO2 ternary phase diagram. So when we looked at the chemistries, the MgO is 90 to more than 99%. So the magnesia, the MgO, is present in great excess in this phase diagram. But the calcium and magnesium silicates that are present are going to be fixed by this lime to silica ratio that I mentioned. So you need a high lime to silica ratio in this material. That eliminates low melting eutectics. And these impurities, lime, silica, the other impurities, perhaps alumina and iron oxide, they're concentrated at the grain boundaries or in the matrix if there's a large amount of impurities. These refractory systems are not really at equilibrium, but they may be in equilibrium at grain boundaries where there's a lower melting phase that may have proper kinetics to reach equilibrium, or at hot phase locations during use. The high temperatures at the hot phase speed up the reaction kinetics. So I mentioned this number 1.86. So the lime to silica ratio, if it's less than 1.86, there's a couple of possibilities here. You may develop liquid phases at 1575 degrees C or 1490 degrees C. So at 1575, there's a eutectic, there's a magnesia dicalcium silicate, and a murronite eutectic. Or at 1490, there's a magnesia murronite monocellite eutectic. I'll go over murronite and monocellite compositions in a minute. But if the lime to silica ratio is greater than 1.86, the lowest liquid phase you're probably going to develop is at 1790 degrees C. This is the magnesia dicalcium silicate, tricalcium silicate eutectic. So MgO is commonly used in steelmaking, lining basic oxygen furnaces. 1790 is a temperature higher than steelmaking temperatures, but 1575 and 1490 is not. So what that means is these phases, these low melting phases like murronite, monticellite, and their corresponding eutectics are going to be fluid liquids at the grain boundaries at these high temperatures. So this is SiO2, MgO, and CaO. And we're right here in this part of the phase field, the high MgO corner here. But if you look at what borders the periclase or MgO phase field, you'll see over here this phosphorite, which is 2-MgO SiO2. That's a fairly high temperature material and a refractory material by itself. Here's monticellite, CaO, MgO, SiO2. Here's murronite. That's 3 CaO, MgO, 2 SiO2. Then we have our dicalcium silicate, tricalcium silicate, and lime. So if you start looking at these temperatures, here you see these lower melting eutectics around 1485, 1502, 1575. So this is what's causing the problem. So this is kind of a summary of that phase diagram, more of a schematic form. It's SiO2, MgO, and CaO. And now the tie lines are drawn from MgO to monocellite, murronite, dicalcium silicate, and tricalcium silicate. MgO to CaO is also a tie line, and MgO to phosphorite to MgO SiO2 is also one. But if you look here, and if you follow the crystallization path in any one of these areas, you're going to see these phases are going to eventually develop. So the lime to silica ratio is 0.93 here. And this one is 1.4 to 1. And then here's your 1.865 to 1. And then this one is higher, 2.8 to 1. So here's monocellite, here's murronite. They're going to form if the lime to silica ratio is less than 1.865. So this table is a good summary of what I just described. There's 9 different cases. This is molecules of CaO per molecule of SiO2, And what I was just describing is in weight percent. This is parts by weight of CaO to 1 part of SiO2. These are the minerals that are forming in their chemical compositions. So here's 1.86. So 1.86 and higher, which is the bottom portion of this diagram, you're just going to have dicalcium silicate, tricalcium silicate, or lime. But if it's less than 1.86, you see there's murronite over here, again over here. Here you have murronite and monocellite, and finally monocellite, and then the phosphorite is going to be in conjunction with some monocellite. These are low melting materials. So the important thing is you have a lime silica ratio in your MgO greater than 1.86 to eliminate these low melting phases and low melting eutectics. So this is the possible eutectics. The first 4 in degree C are 2300, 1850, 1790, and 1800, and the last one is 1860. So all of these are above steel melting temperatures, which is a little higher than 1600 C. And then these 3 are much lower. So MgO and CaO have this high melting eutectic. MgO, CaO, and the tricalcium silicate is also high. MgO, tricalcium, and dicalcium silicate have a 1790, fairly high eutectic. MgO and dicalcium silicate is pretty high. At the bottom is MgO and phosphorite. That eutectic is high, but the ones here, these 3, the lower temperatures, this is MgO, dicalcium silicate, and monocellite, MgO, monocellite, and murronite, MgO, monocellite, and phosphorite. So anytime you have murronite, monocellite present, you're going to have these low melting eutectics. And these are the melting points of the different possible materials in an MgO refractory. Lime is 2570 degrees C. MgO is 2800. This spinel is a refractory by itself. This magnesium aluminate, we'll talk about that next class. It's becoming more popular because it's a high temperature material. 2135 degrees C. Dicalcium silicate is 2130 degrees C. And then phosphorite, another refractory material, this magnesium silicate, which we'll talk about next class, is 1900 degrees C. So these are the high temperature phases, high melting points. Tricalcium silicate, there's a stability region between 1900 and 1250 degrees C. Below and above that temperature, it decomposes to a dicalcium silicate, but it's still a high temperature material, but there's a phase transition. If you have iron oxide present, you can have dicalcium ferrite. That's pretty low melting, 1436 degrees C, so that would be undesirable. Magnesiopherrite, where you'll have your Fe2O3 impurity. That melts at 1713 degrees C. That's low, but it's not too bad. Then monocellite by itself melts at 1487 degrees C. And then murronite by itself, 1577 degrees C. So you definitely do not want to have monocellite and murronite in your refractory material or this particular composition, like calcium ferrite. So there's 2 different ways to control this lime to silica ratio. You can maintain the ratio at 0. Well, to do that, you have to have a very high purity refractory material with basically no lime present. So you might achieve that in some very high purity synthetic sintered materials or fused materials. And if you eliminate the lime completely, you'll have some silica left. So that silica can react with MgO to form that magnesium silicate phosphorite. So that has a high melting temperature. So basically, in this approach, you're eliminating the lime. It's not exactly that easy to do unless you have a very high purity material. But you can also maintain the lime to silica ratio by adding some more lime. So if the ratio is too low, you can add a little bit of lime to bring that ratio up to greater than 2. So now you're forming dicalcium silicate and tricalcium silicate. The dicalcium silicate is going to melt at 2130 degrees C, and the tricalcium silicate at 1900 degrees C. So you can either eliminate the lime or increase it. There are two ways of getting that ratio in a desirable region. So if you plot, this is MOR, modulus of rupture, in megapascals from about 5 to 35 megapascals versus this lime to silica ratio from 0 to about 2.5. And this MOR, the hot strength, was measured at 1480 degrees C, which is still a temperature quite a bit lower than the use temperature for making steel. So at 0 here, you're going to form this magnesium silicate phosphorite. When you're getting up above 2 here, you're just going to have dicalcium silicate and tricalcium silicate. And in between, you're going to have monocellulite and murronite. And this is showing that at 1, a ratio of 1. So what you see here is if you're eliminating the lime, you have a MOR about 30 MPa. If you're maintaining the ratio higher than 2, it's again about 30. But if you have the wrong ratio, a low lime to silica ratio, you can see how the strength, hot strength decreases because of these low melting phases. There's not a lot present, but they're in the grain boundaries. So they're basically coating the MgO grains because they're located in the grain boundaries. One of the good things about MgO in steelmaking, it can tolerate a large amount of iron oxide. So we can look at the FeO MgO phase diagram and the Fe2O3 MgO phase diagram. So FeO is ferrous oxide. FeO forms a complete solid solution with MgO. So the solid solution is FeO, MgO, and FeO is created under reducing conditions. And this solid solution is magnesiowustite. So the Fe is in the +2 ion. So it can tolerate a lot of FeO in solid solution. There's just a gradual decrease in temperature of the liquid formation with increasing FeO content. Then if it's an oxidizing condition with a +3 Fe ion, you have Fe2O3, ferric oxide. So that's going to form another compound known as magnesiopherrite, which is MgO, Fe2O3. And that has a pretty high melting point. We just mentioned that one on a previous slide, about 17, 13 degrees C. So here's the first phase diagram for the magnesiowustite. This is 100% FeO on the left-hand side and 100% MgO on the right-hand side. And the temperature goes from about 2,000 to 5,000 degrees Fahrenheit. So some of these phase diagrams are in Fahrenheit, some are in degrees C. So it makes it a little confusing as to what the temperatures are without converting them. This is the solidus curve, the bottom dotted line here. This is a high temperature, 5,070 degrees C, but you can see the gradual decrease as you increase the FeO content. And this is 2,500 degrees F. And I circled this area here. This is the steelmaking temperatures around 12 degrees F. And if you look at the FeO content at that solidus curve there, that's 70% FeO, and it's still at a temperature the same as steelmaking temperature, 12 degrees F. So anything above 30% FeO, anything above this 70% MgO, which would be less than the corresponding complement would be the FeO. So going from 0 to 70% FeO, you're still above steel making temperatures, and that's going from about 30 to 100% MgO. So it can tolerate a great deal of FeO. The other one, MgO Fe2O3, this is 100% MgO. This is 100% Fe2O3. So pure Fe2O3 melts at 1591 degrees C here. And then you can see MgO around 2800 degrees C. So steel making temperatures would just pick 1600 C. So if you go across this phase diagram, you go from magnesiowustite to magnesiowustite and magnesiopherrite. And I circled this area here because this is your solidus curve, the first one that's approached here, and that's at 1713 degrees C. So if you just look down on this phase diagram, at this 1600 degrees C, the composition can tolerate about 70 weight percent Fe2O3 and still be solid below this temperature, 1713 degrees C. So again, MgO, if it's oxidizing conditions, can tolerate a great deal of Fe2O3. One of the other issues with an MgO refractory is the B2O3 content, the boron oxide content. There's boron in the seawater. The MgO material is made from seawater. And it turns out this magnesia cannot tolerate any boron, really. It can tolerate FeO, Fe2O3, but it cannot tolerate boron because boron fluxes the material. So boron oxide, B2O3, forms a liquid with MgO at this low temperature, 1333 degrees C. So if you have greater than 0.02 weight percent B2O3, you're going to have a material with very poor hot strength because of this trace amount of B2O3. And you can see that on the phase diagram here. This on the left-hand side is B2O3 100%, and then MgO on the right-hand side 100%. And we go from about 900 to 1500. So close to 100% MgO. If we have a trace of B2O3, we just go up here in temperature, and here we see 1333. So any amount of B2O3 in this phase field, the solidus curve is down to 1333 degrees C. So you can't tolerate any B2O3. Also, if you have B2O3 present with SiO2, SiO2 is a more common impurity. We talked about the lime silica ratios, but the SiO2 will react with the B2O3. So silica can't tolerate even small amounts of boron oxide because, again, it's a fluxing agent. So if you have boron oxide and SiO2 in the grain boundaries, liquid is going to form less than 1200 degrees C. And again, the hot strength is going to be very poor with a trace amount of B2O3 in contact with SiO2. So this phase diagram is SiO2 on the left-hand side and B2O3 on the right-hand side. And the temperatures 0 to 1600 degrees C. So a small amount of boron oxide would be just to the right of 100% SiO2. You're not going to have quartz present in a fired MgO, but you may have tritonite or cristobalite. So you can see right here above 800 degrees C, you have tritonite in liquid, and then higher temperatures, you have cristobalite in liquid. But you're forming liquid at a pretty low temperature. if these two are concentrated in the grain boundary. So the MgO refractories have to have the right lime to silica ratio and low boron contents, boron oxide contents. So when you make an MgO refractory, you start out with a dead burn, which is a material sintered at a very high temperature to densify it, or a fused cast material. These processing steps for refractories are all pretty much the same. Of course, the material is crushed, it's sized by some type of screening operation, and then the particle sizes are mixed to maximize the densities, the green densities. And I mentioned there's a processing course later on in this series. Well, in that processing course, we go over the theories for the different particle packing methods. So MgO can tolerate iron, so it's a sintering aid. So you can add some MgO and add to MgO some Fe2O3, small water contents for dry pressing, and then drying and firing. So the temperature range is usually 1600 to 1800 degrees C. When you fire it at the lower temperature, it's known as a conventional MgO refractory. Then when you fire it at the higher temperature, so from 1600 to 1800, it's known as a direct bonded MgO. So the difference between conventional bonding and direct bonding. In conventional bonding, you're going to have coarse MgO grains, you're going to have fine MgO grains. You have a range of MgO grain sizes, and they're going to be separated by the silicate phase. So the silicate phase is going to control the high temperature properties like creep resistance and hot strength and corrosion resistance. If it's direct bonded, now you're going to have coarse and finer MgO grains in direct contact with each other. So that's direct bonding, direct crystal to crystal contact. The silicate phases are going to be higher melting, so more viscous at higher temperatures, and they're going to be isolated. They're not going to coat the grain boundaries completely. So now this direct bonding is going to give good high temperature creep resistance and good high temperature strength. So how do you get direct bonding relative to conventional bonding? You have to start out with higher purity raw materials to eliminate as much of the silicate phase as possible. And you have to go to higher temperatures to grow these crystals and give them crystal to crystal contact. So this is a microstructure of an MgO refractory with a lime to silica ratio of 1. The black regions are the pores. These lighter gray crystals labeled M are the MgO crystals. And then this darker gray region, and in this case, because the lime to silica ratio is low, is probably Monticelli, CaO, SiO2. And that's in this region here. It could be crystalline or it could even be a glass. You can see some direct bonding right here, two crystals in contact, but then you can also see this low melting phase or glass separating the MgO crystals. So the scale here is 0.1 millimeters. So these crystals are about 0.1 millimeters in diameter. And then this is a material with a lime to silica ratio of about 2. Again, the black regions are the pores. These crystals, M, are the MgO crystals. Here's a large aggregate, a polycrystalline aggregate. You can sort of make out the grain boundary. So this is a large aggregate of multiple MgO crystals. And then these are the crystals that are forming in the matrix region during the sintering process. You can see all the direct bonding that's taking place here, the crystal to crystal contact where the grain boundaries merge. So the M's are MgO, the black is porosity, and then there's actually two phases here. This phase that's kind of rough looking, it's a darker gray. That's dicalcium silicate, a desirable high temperature phase. But there's also a little bit of this region, which has about the same color or contrast as the MgO crystals. That's a glassy phase. There's just a little bit of that present also. But the important thing here is there's a lot more direct bonding. So here's an MgO that I looked at. The black would be the pores. You can see a large aggregate here. There's quite a few large aggregates, and in between are the fines in the matrix. And the black is always going to be porosity on these pictures. This is 35X. So in this field of view, we did a chemistry. This is about a 92% MgO refractory, close to 2% CaO and above 4% SiO2 with some iron and sodium oxides present. So you can see the lime to silica ratio is less than a half. So that's an undesirable situation for a high temperature refractory. So we go up to 200X. Here's an MgO larger aggregate. You can almost see the grain boundaries in this aggregate, but you can see the individual crystals of MgO. So all of these darker gray crystals are MgO, and the black again is pores. You can see the lack of direct bonding in this material. You can just look in the matrix, most of the MgO crystals are separated by a second phase, and that's either this phase, the brighter gray, or this phase, the darker gray. So the brighter material, it's about 30% MgO, 35% CaO, and 36% SiO2. That looks like monocellite, low melting phase. And this one, it's primarily MgO 55% and SiO2 41%. That's probably phosphorite. So there's still a lot of phosphorite present, but there's no direct bonding or very little direct bonding in this material. So that's what the structure looks like. The key properties, creep resistance or deformation under load. That's really going to be controlled by the amount and chemistry of the silicate phases. MgO has excellent corrosion resistance in environments where you have a basic slag, so that would be a slag rich in lime. We mentioned that it can tolerate iron oxides, whether it's FeO or Fe2O3. So if some of these materials dissolve in the MgO, it's not going to hurt it. And the thermal shock resistance of this refractory is rather poor. I mentioned it has, of all the refractory materials, it has the highest thermal expansion, 13.5 roughly times 10 to the minus 6 per degree C. That high thermal expansion is a problem with thermal shock because it builds up stresses faster than a low expansion material. So MgO refractories, if they're, let's say they're used to line a basic oxygen furnace, it originally, 40 years ago, 30 years ago, 50 years ago, it was a pure MgO refractory, and it didn't last but hundreds of heats. But now what they're using is a composite material, and we'll talk about composites later. So you're putting the MgO in a carbon matrix. The carbon is non-wetting and has low thermal expansion. So the corrosion resistance is excellent. The thermal shock resistance is excellent. By simply putting MgO in a carbon matrix, and you go from a few hundred heats of steel to 5 or 10,000 heats of steel. So MgO is still a useful refractory, even though it has bad thermal shock resistance. Once you put it in composite form, you have the best of both of these worlds, good corrosion resistance and good thermal shock resistance. And it has good mechanical properties because of the carbon. So here's a couple examples of MgO refractories, a 91% MgO, so there's a lot of impurities here, and then two high purity MgOs at 98%. The densities are around 180, 185 pounds per cubic foot. These porosities are all around 15%. The cold MR is rather good, over 2,000, and the cold crushing is around 10,000, and both of these are in PSI. So good room temperature mechanical properties. The room temperature mechanical properties are not relevant usually to the high temperature properties. Just because it has a good strength at room temperature doesn't mean it's going to have any strength at high temperature. So for the hot MOR, hot modulus of rupture, this is 1100 PSI, this is 1600 PSI. These are fairly high temperatures, 2700 degrees F and 2800 degrees F. So these two have good high temperature properties in terms of strength. This one's not even reported, so it's not available. That means whoever made this refractory didn't report the value because it's probably very low because of the low melting silicate phases that are present. So at room temperature, it's going to have high strength, but as soon as you heat it up, you're going to develop all these low temperature phases and fluid material. So you're not going to be able to report a decent hot MOR. That doesn't mean this can't be used as a refractory. It can't be, you don't really want to use it where you have a high temperature application that requires creep resistance, strength, and corrosion resistance, but you can put it in a lower temperature application, perhaps maybe in a regenerator in a glass tank where the temperatures are low and you using MgO to resist like alkali corrosion. So just because it has low hot strength doesn't mean it's not a useful material. So this one only has 91% MgO and 2% lime, 4% silica. So you can see it right away, the lime to silica ratio is not right. It's only about a half. It has to be greater than 1.86. And it has considerable amount of iron oxide and some alumina. So these are also going to lower the melting point. And so these two have a lime to silica ratio greater than 2. So that's why they're suitable for high temperature applications. And the higher the purity, the lower the amount of all of these impurities. But 1.3 divided by 6 and 1.3 divided by 5 is going to be greater than 2. So that was a section on MgO refractories, very important refractory material. I have a shorter section on dolomite, and we'll go over the raw materials, phase diagram, how these materials are made, what their microstructure looks like, and a few properties. So dolomite, this mineral, MgCaCO3 taken twice, is a solid solution of magnesium carbonate and calcium carbonate. This is a plentiful material. It's a relatively cheap refractory material. So those are some advantages, but the big problem with dolomite, once you convert it to a refractory, you're going to have MgO and CaO. The CaO hydrates rather quickly. So this mineral is a solid solution of the two carbonates, MgCO3, CaCO3. So the Ca to Mg molecular ratio is about 1. It's a high temperature material. Its lowest melting eutectic is 2370 degrees C. And if it's stoichiometric dolomite, 1-to-1 Mg to Ca, it's going to be 30% CaO, about 22% MgO. And then when you decompose it, you're going to drive off the CO2, and that's almost 48%. So it's almost half CO2 coming off when you calcine it. So this is an uncalcined dolomite. There's a source in Pennsylvania. Actually, it's near York, Pennsylvania. It's a very good source of dolomite. There's actually a company there that makes dolomite refractories. And another source is China. So the theoretical loss on ignition, where the CO2 comes off, is about 47. You can see these are close to 47. Theoretically, there's 30% CAO and about 22% MGO. And you can see these two, 31 is close to 30, and these are almost 21. So that's close to this 21. And you're going to have silica aluminum iron oxide as impurities. These are the same materials plus additional materials that are calcined. So now these are MgO, CaO. These are the loss on ignitions, pretty close to the theoretical value, around 47. These are the lime contents. They're 60, 57, 57, and 56, close to 58. And then the MgO contents are in the middle to high 30s. Theoretically, it should be around 41. But you have impurities present in these materials. This one has a great deal of iron oxide present, 6.5%. So again, SiO2, Al2O3, and Fe2O3 are the main kinds of impurities. So you start out with this solid solution of carbonates, dolomite. You apply heat. The magnesium carbonate decomposes first at 775 degrees C. So now you have MgCa CO3 2 times. That decomposes to MgO. You're still having the calcium carbonate present, and then you have some CO2 gas coming off. And then when you increase the temperature to 1870 degrees C, the calcium carbonate decomposes. So you have MgO plus calcium carbonate forming MgO, CaO, and more CO2 gas coming off. So the final microstructure consists of MgO crystals dispersed in a matrix of CaO crystals. And the density of CaO is lower than that of MgO, so it's going to occupy a higher volume. This is not the greatest microstructure because MgO is isolated in a continuous matrix of CaO, and the hydration issue deals with the hydration of CaO. So the MgO is actually protected in this matrix, but the CaO is the matrix, so it is attacked and hydrated rather quickly. So stoichiometric dolomite is about 58 weight percent CaO and about 42 weight percent MgO. So for the raw material dolomite, you can calcine it at 950 degrees C, remove the CO2. You have MgO, CaO. You can take those powders, press them into pellets, and dead burn it, or you can take the carbonate and dead burn it directly. By calcining and pelletizing, you're going to have a better chance of densifying it. The dead burning temperatures 1600 to 2000 degrees C. So dead burning again is an attempt to make it inert and produce a very high density, low porosity, low surface area refractory. So you can plot bulk density versus firing temperature, or porosity versus firing temperature. So if we look at the bulk density, it maybe starts off at 2.5 grams per cc. And then in this temperature region, about 700 to 900 degrees C, you decompose the dolomite, the CO2 gas comes off, the density decreases. These are for two different materials, A and B. They're both very similar. And then as you start getting up to 1400 degrees C and higher, the sintering process takes over, and now you're densifying the material. So the bulk density goes up. The porosity has to follow the opposite trend. You start out with a porosity of 10% or so in the dolomite. As you decompose the carbonates, the porosity goes up to about 50%. And then as you sinter the material, you decrease the porosity and it goes back down to maybe 10%. So that's the change in porosity and density as a function of the firing temperature. And this is what happens to the phases during this dead burning process where you heat treat it at high temperatures. So this is phases present from 0 to 100% versus the temperature. So you start out with all dolomite, this curve here. And as you start to decompose the carbonates, the dolomite concentration is decreasing. And it's 0 at 900. The magnesium carbonate is the first to decompose, so the magnesia MgO content increases. And by somewhere in this temperature, 800 or 900 degrees C, it's all MgO. There's no magnesium carbonate still present. But since the magnesium carbonate decomposes first, you're going to have still magnesium carbonate present, and then temperatures are higher than 800 degrees C, that's going to decrease in concentration. And the lime concentration is also increasing. So finally, above 900 degrees C, you're just going to have magnesia and lime. So that's the sequence of the phases present as you do this dead burning process. Dolomite disappears, MgO first forms, lime then forms, and you have decomposed all the carbonates, and you just end up with MgO dispersed in a CaO matrix. So dolomite is relatively abundant, it's relatively cheap, it's a high temperature refractory material, but there's two big problems associated with dolomite refractories. The first is really the biggest problem is hydration resistance. It's really poor. The lime reacts with water and disintegrates. So CaO plus H2O forms the calcium hydroxide. That's a big volume change and will totally disintegrate a refractory. And I've taken a fired dolomite brick, and you can put it on a table in my lab in Ohio in the summer where it's humid, and wait a month and come back and it's a pile of dust. So just with the moisture in the atmosphere, within a short time, it will completely hydrate and disintegrate. So its hydration resistance is a big issue on how do you use these materials. A secondary issue is the formation of this dicalcium silicate. I mentioned there was a transformation. So there's a beta to gamma crystalline structure transformation when you cool this material. So when you cool it below 725 degrees C, the beta to gamma phase transformation is displacive. There's a 10% volume increase. So why is this a problem? Because you shouldn't have dicalcium silicate present in the starting dolomite refractory. But if you're using it in a furnace and there's a silicate slag present, the silica is diffusing into the refractory, creating a hot phase reaction zone that's rich in silica. It's going to form this dicalcium silicate. So if you have a furnace where the operation is involving heating and cooling, if you cool that furnace lower than this temperature, the hot phase is going to disintegrate. So you're going to lose a section of your lining. So that's a secondary problem, but the hydration issue is the biggest problem. So on the phase diagrams, MgO melts at 2800 degrees C, CaO at 2570 degrees C, and the lowest melting eutectic is 2370 degrees C. All of these are high temperatures, so it's a high temperature material with limited solid solution between the CaO and the MgO. So limited solid solution between these two components, CaO and MgO. And we talked about this a little bit. They both have the same crystal structure. They're both cubic. They both have the same charge. They're both +2, Ca +2 and Mg +2. But the Ca and Mg ions are different sizes. The difference is greater than 15%. So that limits the solid solution that can form. The atomic radius of Mg is 0.65, and the atomic radius of Ca is 0.99, and that's in angstroms. So the size difference limits the amount of solid solution that can take place. So the MgO-CaO phase diagram looks like this. This is 100% MgO. This is 100% CaO. You can see the lowest melting eutectic here is 2370 degrees C. That occurs at about 33% MgO. So when I was talking about the solid solutions, they're on each edge of the phase diagram here. So this is labeled MgO solid solution. So there's a little bit of lime dissolved in the MgO here. And this is CaO-SS, so lime solid solution. So there's a little bit of MgO dissolved in the lime here. So if we draw a tie line from B to C here at 2100 degrees C, and pick a composition A here, 40% CaO, 60% MgO. Point B has the composition shown here, about 5% CaO and 95% MgO. Point B is about 90% CaO and 10% MgO. So here's our starting composition. Let's look to see what happens at 2100 degrees C at this point A. So our lever arms here, this is 41, about 41%. This is about 59%. The composition here, I just mentioned, is about 5% CaO and 95% MgO. This composition is about 90% CaO and 10% MgO. So if we wanted to get the percent of either MgO solid solution or CaO solid solution, we just use the lever rule. So this lever Ca divided by the total Cb is going to be the percent MgO. So C minus A divided by C minus B is about 89% minus 40 divided by 89% minus 5.3. That's 58% MgO solid solution. And then the other one, percent CaO, is AB over BC or CB. So AB over CB is 40 minus 5.3 divided by 89 minus 5.3. And that's about 41%. So right here at this temperature, 2100 degrees C, you have about 41% CaO and with a little bit of solid solution, a little bit of MgO dissolved in it, and you have about 59% MgO with a little lime dissolved in it. It's worth mentioning that two of the impurities commonly found in dolomite are alumina and iron oxide. You can form with alumina and iron oxide, you can form something known as brown millerite. So for CaO, and then your alumina and iron oxide impurities, Al2O3 and Fe2O3, that has a melting point only 14, 15 degrees C. And you can also form a dicalcium ferrite with the Fe2O3 impurity. So it's 2CaO, Fe2O3. That melts at 1436 degrees C. So some of these impurities can actually hurt the use temperature. So when this is made, you start out with a dead burned dolomite, MgO-CaO. Again, it's crushed, screened, and mixed to maximize the particle packing for density, maximum density. And these materials can tolerate Fe2O3, so it's a possible sintering aid. It may be added to promote the sintering process. You can't use water with these materials because they hydrate, so you have to use a non-aqueous binder. So it's dry press. There's a drying step and a firing step. Firing is usually between 1400 and 1700 degrees C. And as soon as these are fired and they're cooled down out of usually a tunnel kiln, you have to do a moisture protection. So basically, they're shrink wrapped in plastic, and then they go into cold storage in an air-conditioned cold storage facility, a low moisture content facility, and they'll last 3 to 6 months under those conditions. So the idea here is you have to get these after manufacturing, you have to get them in a furnace lining within 3 to 6 months. And as soon as you get them in the lining, you have to heat that furnace up. Once it's at temperature, it's not going to hydrate. It's going to be fine. So there's some logistic issues here on getting these into a furnace as fast as possible and getting up to temperature. If you can do that, you have a relatively cheap, very good refractory material. So the sintered product is, again, I mentioned MgO crystals dispersed in a polycrystalline CaO matrix, which means the CaO is not protected from hydration. If it were reverse, that would be a better situation. And you can also have, in these sintered products, direct bonding, direct crystal bonding, because the CaO crystals are in direct contact. So there's basically direct bonding in the matrix. So this is what the microstructure looks like. The dark areas are MgO. The light areas are CaO. And you can barely make out the grain boundaries in the CaO matrix. You can see these little black spots. They're internal pores in the lime matrix, the lime crystals. But you have MgO crystals dispersed in a continuous lime matrix. The bar is 30 microns, so these crystals are fairly small. These are 5 to 10 microns. Maybe the CaO crystals are a little larger. So properties, thermal shock resistance is a little better than an MgO refractory because the lime addition lowers the thermal expansion of MgO. It's still not great, but it's better. But it has very good corrosion resistance when you have a basic environment or a basic slag. So it has very good corrosion resistance. These may be used in a cement kiln for the lining, some type of refining furnace. There can be used in AOD vessels, argon oxygen decarbonization vessels. You can also take a dolomite refractory and add MgO to it to enrich it to get a higher MgO content, and that improves the hydration resistance. So these densities are in the 180s pounds per cubic foot. These have porosities around 12 to 14%. The cold crushing is rather good. This is 5,000. These two are around 10,000. That's in PSI. And they have good hot strength. These are 1,000. These are 700 at 2550 degrees F. And these are the corresponding MgO and CaO contents. The enriched one has a little bit higher MgO content and a little bit lower CaO content. But they're typically in this 40 to 50, 40 to 60% MgO range and 30 to 55% CaO, 30 to about 40% CaO. So the CaO content percent-wise is less, but it's less density, so it's going to be more volume. So that's what I have on MgO and dolomite. Then this will continue next Monday. Again, thank you for listening today, and we'll finish up the basic refractories next week. Again, thanks for attending.